And we're back. All right, ladies and gentlemen. So again, this is where it starts to kick into gear a little bit. Starts to turn into more calculus than just pre-calc in Algebra 2. Okay. Today we're going to talk about the limit of a function. The limit of a function. Okay. The limit of a function. Now I asked Mr. Delap, and he said, yeah, I might have mentioned it a time or two because I asked, did you teach limits? And he said, nah. He said, I didn't really teach it. I didn't really go through it. He said, maybe I might have mentioned it a couple times. So I'm just going to start from the bare minimum. Yesterday we were introduced to that problem where I wanted to make that point as close as I possibly could. So some might say sufficiently close to be able to say, well, if the slope between these 2 points is this, then I can say the slope at that point is the same thing. Because the difference between the point that I chose and the actual point was negligible. It was sufficiently close. Okay? That idea is taking a limit. It's taking the difference between those points and trying to send it to zero, trying to make it zero. Can I actually make it zero? No. I can't actually make it zero because if I would actually make it zero, well, then the denominator would come out to be zero, and it's not working out, right? Okay, so that's the idea of the limit of a function. Now, having seen in the preceding section how limits arise when we want to find the tangent to a curve or velocity of an object, we now turn our attention to strictly limits in general and numerical and graphical methods of computing them. Let's investigate the behavior of this function, x squared minus x plus 2. Now, you don't have to write this down. It's just kind of like taking a little bit more, taking a different look at another function. Now, we looked at just the plain old x squared. Now let's take a look at x squared minus x plus 2. We know it's the y-intercept is up 2 units. We know it's still a quadratic, so we know it's U-shaped. This is the diagram down below, to the left of the table. So what if I wanted to find the values near 2? Not at 2, but near 2. Well, think about it. Well, if I wanted to investigate it at 2, I could look at all the points leading up to 2 from the left side and look at all the points leading down to 2 from the right side, correct? I could look at 1, then 1.5, then 1.8, then 1.9, then 1.95, and so on and so forth. And when I do that, I see a pattern arise. What does it look like it's approaching from the left side? 4, right? I make x continually closer to 2, sufficiently close to 2, and the output gets pretty close to 4. Let's look at it from the other side. Okay, now look at my x values here. I am taking it at 3, 1 unit above on the upper side, and I am making it smaller and smaller and smaller. I'm saying, okay, let's choose 3, let's choose 2.5, let's choose 2.2. And what am I doing? I'm just finding the value, just plugging that in to the function. Okay? If I plug in 3, it looks like I get 8. And I decrease it, and I decrease it, and I decrease it, and I make the margin between the number that I choose and 2 smaller and smaller and smaller. I send it to 0. I want to make it 0. And when I do that, I see that the output value gets sufficiently close to 4. It gets very, very close to 4. So we can say that the limit as x approaches 2 of this function is 4. That's how we can read that. That's what we can say about that. We can say that the limit as x gets sufficiently close to 2 is 4. Now, did we ever calculate the value of the function at 2? No, we never actually did that. Could we in this one? Yeah. You plug in 2 to that function, what do you get? 4 minus 2 plus 2. Oh, 4 minus 2 plus 2 is 4, right? So I can actually calculate the value of this function. So this seems like kind of ridiculous to do this. But that's the idea of a limit.
Your attention, 7th graders, at this time, students' last names beginning with M and N. Please go to the pause now for your help screening. That's 7th grade students' last names beginning with M and N.
Just a
Please
minute.
go to the pause now for your help screening. Thank you.
All right, so this is the notation that we can use. This is the notation that we use. We write LIM x, and tell me what it's going to. The limit as x approaches 2. And then inside the parentheses, we write the function that we are investigating. And then on the other side is what the function is leading to. Okay, so this is how we read this. The limit as x approaches 2 of x squared minus x plus 2 is 4. Okay, that's how we read that. So here's our intuitive definition. This is how we are going to define a limit. First of all, f of x needs to be defined when x is near the number a. And that's actually an important statement, and you have to kind of analyze it to think about the importance. F of x needs to be defined only near a. Did I say that f of x needed to be defined at a? No. I only said that f of x needs to be defined near a. This means that f is defined on some open interval that contains a, except possibly a itself. Like, it doesn't need to be defined at that value. It just needs to be defined around, near a. And I don't want to say above a or below a, because you want to look at it from above and below. It needs to be defined both left side, right side. Then we can write the limit as x approaches a of f of x is L. That's saying the limit as I take x and get it closer and closer to some value a, like we did 2 in the last one. The limit as x approaches a of f of x of the function, you always have to define what function you're using, is equal to some number L. The limit of f of x as x approaches a equals L. If we can make the values f of x arbitrarily close to L, or sometimes the book says sufficiently close to L, as close as we may like, by restricting x to be, here they use that, sufficiently close to a, on either side of a, but not necessarily equal to a. Right, that's just what we looked at before. We said we're going to take x and send it to 2. Make it closer and closer and closer to 2, both from the upper end and the lower end, to squeeze it in. And we have an upper boundary and a lower boundary, and it's going to get good until we can say, that's close enough. We can kind of get what it's going to go to. Okay, that's the idea of a limit. Sometimes we are able to evaluate at that moment. That is actually, we'll learn a little bit later on when we talk about operations with limits. That's called direct substitution. When you can just plug in that a value right into the function, there's a limit. Okay, perfect. Okay, that's the easiest way to evaluate a limit. But a lot of times it's not defined at that value. So what do we do then? Well, that's like that's all the beginning of chapter 2. Okay. Yeah. So I kind of talked about this already, the fact that it doesn't need to be defined at that place. And I wanted to show it graphically as well. Okay, so this is all, we can calculate the limit in all of these scenarios. Okay, we can actually calculate the limit in all of these scenarios. Take a look here. What if I wanted to evaluate the limit as x approaches a of this function f of x? So I want to evaluate the limit as x approaches a of this line, and it's going to equal some L. Okay, so that means I'm going to run values sufficiently close to a, both from the upper end and the lower end, to see where it's going to converge to. Does that change at all if I remove that point? If I do that same calculation, am I going to get a different answer? No, because I'm still taking the same function, I'm still running those same values, and it's still going to lead me into the same direction. Now, the weird part about this one is this is actually called a discontinuity. We have removed that point from the function and put it somewhere else. Weird. I don't know what, we'll look at functions that do this. Normally they're piecewise. But I've taken out that point and I've put it somewhere else. Does the limit change when I do that? No. Because it's still going to lead into the same point. Even though the value of f of a is not L, The limit is still L because it's, again, focused on what's near L, near A, but not at A. Does it change when I remove that point altogether? You know, this, we took the point and put it somewhere else so that the function was still defined. Hi.
I need Ashley Miller, please.
There you go. So the function was still defined, but not necessarily equal to that point out there. So what if it's undefined altogether? What if, like, we don't even know what it's going to be? It's not even defined. Still doesn't matter. The limit as x approaches a of the function is still going to converge to L. No matter if the point is there, the point is somewhere else, or the point is not even there at all. The limit is still going to converge to the same thing. Okay. All right, let's take a look here. I love this. Guess the value. Guess the value. I don't know. 4. Done. No. I don't even know what it is. You should look. The limit as x approaches 1 of x minus 1 over x squared minus 1. You know, I talked about just plugging it in being a possibility. Can I plug 1 in? What happens if you plug 1 into the function? You get 0 in the denominator, right? I get 0 over 0, which is undefined. So I can't just directly substitute. So what do we have to do? Well, we have to run values that are very close to 1, right? Run values that are really close to 1. So let's start, I don't know, 0.9. That's pretty close to 1, right? So I'm going to say, now I'd like to just keep entering this in my calculator, so I'm going to be very careful with plugging this in. I got 0.9 minus 1 in the numerator divided by, okay, I'm going to put this in parentheses, 0.9 squared minus 1. Everybody follow me there? I'm just going to look at it from the lower boundary. I don't know what this is going to go to. Okay, cool. That tells us really nothing yet, because what we need to do is see where it's going to lead to. I got to make sure I'm plugging this in right. 0.9 minus 1 on the top divided by all the chunk of 0.9 squared minus 1. Okay, good. Let's do 0.99. Let's insert a 9 in there to make it 0.99. Insert a 9. Okay, that tells us something. It went from 0.52 to 0.50. Where do you think it's converging to? Where do you think it's going to go to? Maybe 1/2? Let's see if that prediction is correct by adding in another 9. There we go. So this is 0.999. Okay. I think our 0.5 value is looking good. Yeah? Now, you know what we should also check? The upper boundary. So we believe that from the lower side, it's going to converge to 0.5, but I guess we should check from the upper side as well, right? So if I say we want to do maybe 1.1. So I'm going to go back in here, and instead of these 0.9s, whatever, I'm going to do 1.1. Delete away that 9, and I've got, oops, one too far, 1.1, and delete away that 9. Okay, yeah, that makes sense. It's below 0.5 because as I was approaching x, or as I was approaching 1 from the lower side, it was getting me to 0.5, and it was going like downward to 0.5, right? So if I skip to the other side and I'm now converging the other way, it's on the lower boundary of 0.5. Let's do that one more time. And now let's add in a 0, 1.01. Insert a 0. To insert is second delete. That INS is insert. Insert a 0. Did we get closer to 0.5? Yeah. So we can guesstimate that the value of the limit as x approaches 1 of x minus 1 over x squared minus 1 is 1/2, 0.5. These are the tables that the book gives. Okay, they started at 0.5 and then went from 1.5. That went a half unit above and a half unit below. And we can see it converging to 0.5 on both sides. Now, the unique thing about this is that, we've looked at rational functions before. Could I reduce that function down? Right? I just factored. And what can I do top to bottom? Beep, beep. Cancel the x minus 1s. Okay, let me ask you. Can I evaluate the limit as x approaches 1 of this function? Because isn't that just a reduced form of that? Can I plug in 1 now? What do I get when I plug in 1? Oh, this side. 1/2, don't I? So what you can do is actually reduce them down, then directly substitute, but we'll talk about that a little bit more later on. See, some of them you can reduce down. Now look at the graph. Doesn't this make sense that there's a hole in the graph at x minus 1? We can cancel out where we cancel. There's holes, right? So even though 1 does not exist in the domain, I can still calculate the limit as x approaches 1 of that function. Okay, that's what I'm showing you here. Even though there is a hole at 1, the limit as x approaches 1 still exists, and we can still calculate it. Okay. This is kind of doing like the major labor-intensive way of doing this. The rest of the beginning of chapter 2 is all about, okay, how do we streamline that? There's got to be a better mathematical way to do that, and then in comes direct substitution. Now, just to kind of change it up a little bit, what if I had made this a piecewise function? Because we had seen that 1 does not exist there, right? We had seen that 1 does not exist for that function that we just looked at. It's undefined. So what if I defined it to be something else? What if I said, okay, let's make this a piecewise, and said, now, if I say, if x is at 1, let it be 2. I don't know, something weird. Look how it's graphed. Right? So you got this funky, looks like a decay almost, right? But at 1, I assign the value of 2. Does the limit change? No. The limit as x approaches 1 of this new function g of x, and you can do this. This is okay to do, like if you have some weird wacky function and it's like piecewise and it's defined somewhere else, you can just say like g of x. You don't always have to put the function in there like we did here. Okay? So we said, okay, let's make this new function g of x where we define 1 to be something else, 2. Well, then the limit as x goes to 1 of g of x, well, I would still be doing the same operations, right? If I chose 0.9, would I be looking at 2? No, I'd be going up here, right? Because my piecewise says, well, if it's not 1, then use this. So if I chose 0.9, I'd still be going to that and plugging it in. If I chose 0.99, I'd still be going to that and plugging it in. If I chose 1.1 or 1.01, I'd still be going to that and plugging it in. So even though the limit is defined to be something else, the function is defined to be something else at that value, the limit is still going to calculate the same way. Okay? The limit would still be calculated the exact same way. It's still going to approach 1/2 for that. Even though g of 1 is 2, the limit is not 2. The limit is actually 1/2. Okay. All right. We're actually going to look at this function a little bit later on. This is a weird one, isn't it? Why am I showing you this one? I'm showing you this one because this one doesn't even reduce down at all. Like the other one reduced down and we could directly substitute. Now, you've got to run your values till you can see a pattern. Do you need to like go crazy and make a giant table that the book provides? No. You have to go until you see a pattern, until a pattern arises. Okay? Now, I want to make t go to 0. Let's go with the upper boundary. What do you want to choose first? What do you want to choose? 1? Let's go lower. Let's go 0.1. Why not? Because does it matter? Does it really matter if you start at 0.5 or 0.1? Just as long as you make another calculation beyond that, even smaller, you know? Could I start at 0.001? Sure. Then the next time you run it, go 0.0001 or whatever it may be, right? So now we got to be careful plugging this in.
Attention, 7th graders. At this time, students' last names beginning with O through R. Please go to the pause now for your help screening. That's 7th graders' last names beginning with O through R. Please go to the pause now for your help screening. Thank you.
I missed a parentheses. I got to put this whole top chunk in parentheses, right? The square root of t squared plus 9 end cap minus 3 divided by, and then I'll just put this in parentheses for good measure, 0.1 squared. Okay, ready? Okay. Now, let me ask you something. No, I'll talk about that in a second. Let me just run this value next. So let's do the same thing of 0.01. Okay, because I saw 0.1666. Okay. I mean, maybe in those two calculations alone, you can see what it's converging to. What do you think it's converging to? 0.16 repeating. 0.16 repeating. If you wanted to make another calculation, go for it. Okay, we could run it again. Just 0.01 in there. Yeah, it actually rounded. That's funny. It actually rounded it off. It's stopping because the calculator is a very dumb, smart object. The calculator sees what it's converging to, and it's like, I'm going to stop because that difference is so small. Okay, that's actually kind of interesting. Now, this is what I was going to talk about before. So we could say from the top end, it looks like it's converging to 0.16 repeating. Okay, 0.16 repeating. From the bottom end, look at the equation. If I were to plug in negative 0.1, wouldn't that evaluate to be the exact same thing as positive 0.1? Because I'm squaring it, right? If I evaluated negative 0.01, it would come out to be the same thing as positive 0.01 because I'm squaring it. So actually, this is what the book shows, plus or minus those values. Okay. So we can say that this is going to converge. So the limit, actually I should say this, limit as t goes to 0 of this weird t squared plus 9 minus 3 over t squared is actually equal to 0.16 repeating. And that's all that we know how to do right now. All we know how to do is just kind of plug and chug and say, I think it's going to go here. My table is telling me that it's going to, my calculations are telling me it's going to go here. But we don't know for sure. Okay. And mathematicians hate that we don't know for sure. So what we're going to be doing in the next couple sections is figuring it out. We actually look at this problem again and evaluate it in a little, cleaner way. Okay. Oh, what time does this period end? 9:17? Yeah. Let's look at one more. Okay, the sine of x over x. Can I just directly substitute 0 in? Like, can I evaluate sine 0 over 0? No. 0 does not exist here. Okay. Well, if I plug in values pretty close to 0, I'm going to say sine of, well, where do you want to start? 0.1 again? 0.1 divided by 0.1. Okay, that's all well and good. Tells me where it's close to what it is close to 0.1. But let's run another value. Let's say 0.01. Insert a 0.01. Insert 01. Okay, maybe you can see it from there. What do you think it's converging to? 1. Let's see it from the bottom end. Let's do that same value, but instead make it a negative. Insert a negative. Insert a negative. I guess I should have started. Oops. Whoa. Insert a negative. What the heck happened? 0.01. Okay, good. Oh, look at that. Just like the one I had before, the negative and positive are evaluating to be the exact same thing, aren't they? So what can you say the limit as x goes to 0 of sine x over x is? What do you think? Who knows? Yeah, they're showing you a bigger table here. You don't have to run all those calculations. All you have to do is run some numbers to see where you think it's going to go to. Okay. All right, we'll stop there for today. We got a lot to do on Monday, but we'll be all right. I'll get moving on Monday.